By the way, we have a YouTube channel right now for all the videos we upload. Okay, okay, let me start. So thank you for joining me today. Today, the topic is about graph rewiring. Um, so I'm gonna define this term later on, but I just want to start with the list of papers I want to go over. Basically, you can see that this is trying to address some common challenges in GN learning. And then the topic of rewiring focuses mainly on the graph structure, such as you can see some keywords like transformers, positioning, encoding, diffusion, and so on. And then I will also talk about the geometric perspective on this one, something related to differential geometry, which we went over previous reading group. So first we go over the three major main challenges in GN. So first one is called underreaching. This means when you have a large graph and you need to propagate information to all the nodes, but you have a very shallow GN. So this is commonly addressable by using deeper GNs. And then the second one is called oversmoothing. It's basically talking about all the node embeddings become somewhat uniform because after some long time of message passing, they sort of learn only the features of their computational neighbors. So so techniques to address oversmoothing often involves changing the learning algorithm, such as using a different scheme for message passing and so on. So the focus of this time is the over-squashing problem, which I will talk about in detail in a later paper. But this class of problem often concerns with the modification of the graph topology or the graph structure. It's basically some problem with the graph itself, so we have to modify it. So this is the first paper I'm going to talk about. It basically introduces the idea of oversquashing. So the way they talk about this problem is first they make this analogy with the sequence-to-sequence model in NLP. Basically, you have the encoder-decoder model, and then your the hidden states basically get updated every time, and then your decoder needs to sort of process the final state of the encoder uh, to learn to decode basically. So all those information would just go over to this one node in the middle, which would they call as a bottleneck. And they claim that with the graph, it is actually a much worse problem because the graph neighborhoods can grow exponentially. So if you have some graphs, let me give you an example, such as you have two giant communities and then there's like one link in between, then the link in between will sort of be like a bottleneck because it's gonna propagate all the messages from that one community to the other one. So
So
so they
Fred, can you
yeah.
help us to understand what's the meaning those nodes will be called as bottleneck? Because from graph perspective, but indeed some of those nodes, they like high degree, um, lots of message can be passed to it or through it. But why this is a problem?
Okay, so let's just understand it for perhaps from the information perspective. We have a finite dimensional vector, which we use to represent the node embeddings, right? So, so if we have a lot of information to fit in this finite sized vector, then the more information we need to aggregate, then hopefully we should use higher dimensional vectors, right? So this is basically saying that if you kind of have a not too high dimensional vector to embed your nodes, then if all this information goes through, then you sort of have this bottleneck, sort of like you have a bad internet connection when like too much traffic is going in, something like that.
Yeah, that makes sense. Meaning that when we aggregate other information, then we cannot differentiate those information anymore because somehow given the fixed dimension of that vector, right? So we ask too much.
Yeah.
Okay, great.
So they try to study this phenomenon using this QM9 dataset, which is a quantum chemistry dataset, because the hypothesis is that datasets that concern with biology or chemistry often rely on long-range interactions. So so that if you have this kind of bottleneck structure inside, then the long-range interaction could be hampered by these bottleneck nodes. So this data set basically contains about 130,000 graphs. Each is like a molecule and then a relatively small size molecule with on average 18 atoms. And the edges of these molecule graphs would be the bonds between the atoms. And the goal is to try to predict three real-valued quantum chemical properties. So to avoid the first problem of underreaching, they basically use a GN that's deep enough to reach the graph diameter. Basically, this means every node can receive messages from like the all other nodes in the graph theoretically. So they basically want to compare the performance between the original GN without any modification with another special type of GN, which they call like a GN plus a fully, I don't know what is the FA represent, but it's basically saying that in your last layer of GN, instead of doing the neighborhood message passing, you aggregate all the information from all the other nodes. So so you essentially have a fully connected graph, a computation graph in your final layer of GN. So this very simple modification actually brings a big performance in consistent performance across all the 16 targets in terms of the MSE, I think. Yeah, so this is basically them showing you like proving, not really proving, but verifying that such phenomenon does exist. And you need to rewire the graph to make the information flow more freely to get a better representation. So naturally, and here are some other results that are also showing you the consistent improvement on some biological data sets. Enzyme and the second one I think is, yeah, it's about computer programs. Yeah. So naturally there are some discussions about, because the information bottleneck we talked about earlier, it could be just that you can increase the dimensionality of the node embedding rather than modifying the graph structure. So is modifying the graph structure really necessary? So they did this experiment to compare the performance improvement of simply increasing the node embedding dimension versus changing the graph structure. And they found that changing the graph structure has a much greater improvement of the performance than simply increasing the doubling the node dimension. And then they also studied in the second part how fully connected you need to be for your last layer. And they found that indeed a fully connected layer is better than if you have a more sparse connection. So what about you simply get rid of the graph structure and just use a fully connected graph? So they show that if you simply do that, you're giving up a very good inductive bias introduced by the graph structure. And that actually results in a very much worse performance. So you can't simply get rid of the graph. Therefore, we see that we need to modify the graph, but we do not want to completely get rid of the graph. So now I want to basically sort of define what this graph rewiring term means. It is appearing in some papers. It could be termed differently in some other papers, such as I guess structural learning. But the early observation is that we need to decouple the computation graph and the input graph data, because the vanilla GM basically you treat the input graph as the computation graph. You treat the message passing with the neighbors in the original graph. So they say, so, but we can see that even in 2017, the Graph Sage paper, they do some neighborhood sampling to address scalability issues, also generalization issues. So they kind of decouple the computation graph with the graph data. And then later on, I will also go over this graph diffusion convolution paper, which kind of uses diffusion kernel to modify the graph structure before applying the GNN. So naturally, like if we want to change the computation graph, then why don't we just use the transformer? Because transformer is like the most complete example. You just care about all possible information in your graph, right? You can sort of think about transformers computation graph as that of a fully connected graph. So here there's a second paper talking about is this 2021 paper called Do Transformers Really Perform Bad for Graph Representation? So we already see that in the bottleneck paper, they talk about if you simply use a fully connected graph, it actually make the performance worse. So this paper says you can still use a transformer, but then you need to do this positional encodings for the nodes, because by using a transformer, we kind of get rid of the inductive bias of graph, but we still need that. And the way we do that is to use positional encoding. So the high level idea is that they add this centrality, which is the node degree as a node feature. And then they use some like shortest path aggregation method, which I'm going to talk about later on, and some edge encoding to preserve some graph structure information. So the first thing they would do to try to add some structure information in their transformer is that they add additional like node feature to using the information of the in degree and out degree number for each node. So because the degrees are just the scalars, and the node embeddings of vectors, they try to do some. They try to add an embedding layer to each of the scalars. Like for example, the z minus and z plus here, they're actually, for example, if xi is like a d-dimensional vector, then the z's are also d-dimensional. This is like obtained using some learnable embedding layer. And then they want to use the graph shortest distance to assign some additional terms in their attention matrix. And the way they do it is they use the shortest distance between two nodes as a additional feature. And then they again added a learnable bias that's indexed by this number, and they add it into the computation of their attention computation. And the third modification they have is to also add some like even one additional term, Cij, which is some kind of aggregation of like edge encodings, because you kind of assume that your input graph has edge features as well. So they try to also incorporate the edge features using the shortest path. So by doing all these steps, they change their attention matrix to sort of incorporate both the node information and the edge information in the original graph.
So I have a question here. In the transformer that applies to text setting, we need to set up the window size. So in this setting, it seems like we wanted to include all the nodes in the graph. But how is it possible for very large graphs? Or it's just still in like chemical compound setting?
Yeah, I think that's a good question. So for large graph, I'm not sure how large you are talking about, because in the end, we still need to deal with the adjacency matrix, right? And here the attention matrix is basically just the you can think about it as the adjacency matrix. Um, yeah, so
I think the question here is that you have to compute the shortest path among every
yes,
pairs. So here the Floyd algorithm takes about n
okay, yeah. The Floyd Warshall is like
yeah
cube, right?
cube
Yeah.
complexity. So I know the author of this paper, so I asked him about this question, and most data sets he deals with is molecular data sets, which involves about less than 20 molecules per graph. So I think yeah, how to scale this kind of algorithm to larger data sets is a problem here.
Hmm. Okay.
Okay, great. Yeah, thanks.
Thanks. Yeah, so this is just basically the pictorial kind of summary. You have additional node features, and then you sort of involve the edge features and the shortest path feature into the computation of your attention. So they basically showed their performance on a couple uh, biology and chemistry data sets, and at that time they achieved the state of art. Right. So, and then there's one interesting thing that they talk about in their appendix, which is they say positional encoding is important. It's one way to have your GN learn something more than the traditional message passing GNs that rely on the one Weisfeiler-Lehmann test. Basically, the traditional GNs that only rely on neighborhood information, they are not able to sufficiently distinguish two graphs, determine whether they're isomorphic. But if you add positional encoding, you can do more. And they give the example here. Yeah, I think this is just an interesting observation. The two types of nodes in the left graph, I think it's like basically, let's see. Yeah, so basically, I think if you do positional encoding, you can distinguish them. Yeah, because three. Yeah, I'm not sure exactly the details here, but yeah. Does someone know like maybe what this means? The count? Okay,
What
this one.
uh, oh, you mean distinguish from
Yeah,
those two
yeah,
sets,
yeah.
right? Also, actually there are so these graphs are not
Yeah, they are not isomorphic.
but if you just use one-dimensional Wheeler-Lehmann test,
Yeah.
it will give identical
Right, right.
yeah, graphs. But if you empower, so if you give additional features with shortest path between other kernels, right? And actually you can, with that kind of additional node features, you are able to distinguish the two graphs.
I see. Yeah, that makes sense.
Yeah.
This is using shortest path as additional.
Yeah, as additional features.
Yes, yes. Thank you. So yeah, so this basically says that, and you can sort of think about the shortest path as kind of you know, embedding your graph into some metric space. So it's sort of like some additional mathematical information that you can exploit. Yeah. And then there's some natural extension to the transformer-based approach. But basically, this paper talks about how you don't have to do like a fully connection on the entire graph. You can simply do some local fully connections, such as like a R-ring connection, which is like the R-hop neighborhood of a node. Like you kind of do a fully connection there and see how that works. Yeah, so basically, you don't use fully connection, you use these local connections. Yeah, and they found that using some small values of R could work for, depending on your problem. Some short range problems only require one hop neighbors, and some long range, you probably need more, like a bigger R. And they also did add some like additional steps to the construction of this new graph. first they connect all these, for example, for one node, they connect the local R hop neighborhood, and then they add a new like pseudonode classification node to connect all the nodes for a graph-wise classification task or something similar. Yeah, so I think this paper was really interesting is that they kind of talk about different ways you can do encoding for the edges in this case. First, so the option one is shortest path encoding. You can, for example, for a node and its R hop neighborhoods, you can assign number integer from 1 to R to each of the to the edges. And if you use PE equals 1, that basically means the original graph edge. And then all the additional ones, the 2-hop connection, basically like you directly connect this node to the 2-hop neighbor. You directly connect the node to this R-hop neighbor. So you got these new edge features. So this kind of encoding is lossless because you can simply use edge encoding of 1 to determine the original graph. So the original graph can be recovered. The con is that the different different edges can have the same positional encoding. And the shortest path itself does not capture some complex inductive bias, such as multi-hop diffusion.
So Fred, I still have some difficulty understand the position encoding here, because if we have a sequential structure, things kind of easy, right? So you just because you have the linear order, you can easily label them as 1, 2, 3, 4. But now we have a graph. So depending on the starting point, then the position is going to be rather different.
Yeah, so this is with respect to each node, I guess, because yeah, it's a little bit difficult to draw, but so if you have like these two are the 1-hop neighbor and this one is the 2-hop neighbor, then basically they add this new one. If R equals 2, they add this new one to this new nodes to add these new edges, and then this would be 1, this would be 1, and this would be 2, something like that. This is their this first kind of encoding scheme, and one basically allows you to recover the original graph. I think the question would be,
here the position encoding is added to the edges, including the original edge and the kind of path, right?
Right.
So, and that number just means whether they're directly linked or they could be linked with a 2-hop, within 2-hop or 3-hop.
But they added this edge in their computation graph, so they do directly propagate the information from here rather than from the intermediate.
But this essentially just add length 2 paths to the original graph.
Yeah, this is one way to do this kind of encoding.
So they want to add length 2 or maybe length 3 paths to the original graph, and then they will label those additional edges as 2 or 3.
Yeah.
Okay. So that's a way to augment the original graph.
Yes, that's one way to augment it.
Right. So to me, it's just like you try to increase your receptive field by adding those extra neighbors, right?
Yes. So I think the entire changing your computation graph is to try to expand your receptive field, because you can, by doing that, you can have more paths to pass information to you rather than going through that bottleneck. Does that make sense?
Yes, that makes sense. Is which I think you are introducing multiple papers for this idea. Which paper does it belong to?
So which paper does this one belong to?
Mhm.
Oh, this is this paper. So this paper actually they didn't publish it. Yeah, but this professor is the professor we took the shape analysis class with. If I don't know if you remember,
Mhm.
I just think that this is a very natural extension, and they did some experiments on this parameter R. And I think the reason why they didn't publish is because they didn't beat the state of art. But still, I think it's some interesting work.
Okay, thanks.
So, and then they talk about the another possible way to do the encoding, which is they use the Laplacian eigenvectors. Um, so, so you can see that Laplacian is the Laplacian matrix is basically the spectral representation of the graph. So so implicitly this is embedding the graph into a Euclidean space because I think the Fourier space is like it's kind of like a Euclidean space. Um, yeah, and then basically this is like using your global graph information to add additional node encodings. So it can reflect the diffusion process because the Laplacian describes the diffusion, but it is not injective. You can't really recover the original graph if your original graphs are isotropic. Something, yeah, this is just like a jargon term. And they also say that this is not really an issue. Like you can't really find a lot of isotropic graphs.
So they used these spectral encodings for the molecule graphs.
Yeah.
Okay, then there's a problem, right? Because you have many different graphs, and they have different adjacency matrix. The spectral embedding doesn't naturally transfer between different graphs, right?
Yeah, I think you mentioned a very good point here. So actually the spectrum, so I mean the eigenvalues of different graphs, they vary very greatly, right? So there is an upcoming, there's a follow-up work called Rethinking Spectral Attention for Graph-Based Transformers appears in last year's New York that solves this problem. Yeah, I can share this work with you later.
Mhm. Okay. Okay, thank you. Right, and then the one additional thing they do is they use the powers of the adjacency matrix because the adjacency matrix raised to the kth power it's basically talking about the number of lengths k paths between two nodes. So yeah, again, this is lossless because your original adjacency matrix is included, and it gives some kind of encoding that reflects connectivity. And they end up using this one for their experiments. And yeah, so they didn't beat the state of art, but what I found interesting is that they kind of show that in different tasks, different choice of R give you different performance. It's not that the more connections you have, the better, but it's about whether your connections, your added connections can reflect the problem you're dealing with. For example, for this, I think this is the graph CFR10 data. Um, the the kind of information you need in your graph learning is perhaps only a very local message passing. So the higher order ones are actually not as useful as, for example, in the molecule and the biological cases. Yeah. And then, so that paper, after that paper, there's this one that's also using positional encodings. But what's interesting in this one is that they try to also learn the positional encoding, because you can see from the previous one, they're simply using some existing graph level features of the input graph. They didn't do any learning. So this one, they actually do learnings with the positional representations at the same time. So and they also reason about using it for in the framework of a general message passing GNN. So here,
Sorry, I have a question. So for the previous paper, once they create that second hop, third hop, like higher order R edges, they didn't learn any encoding for that specific edge.
yes, they didn't learn encoding.
Okay, but they still call it positional encoding.
Yes.
Okay, yeah, then yeah, I misunderstood for the entire time. I thought for different R there was an encoding that's learned, but seems like they are just doing those like extra connections.
Yeah.
But
Yeah.
it could be learned as well. If you, for example, you can scroll down to this paper, right? Actually,
Yeah, so
this paper you can plug in
Yeah. This paper is learning that.
okay. Yeah, I saw the previous paper is doing what's showing on this page because
I
I feel the name was a bit confusing because
Yeah.
they call it positional encoding. Yeah. Yeah, anyway, just want to clarify. Thank you.
Yeah. Yeah, so this one they do learn the positional encodings, but still, like you see, one additional thing is that this one is not just learning it with some initial embedding; it also learning it alongside with the features. So let's look at the standard message passing GN with positional encoding. This is basically the standard layer by layer update for the node features and the edge features, right? The difference between adding positional encoding and not adding positional encoding is that your input feature has the input feature in addition the positional encoding in addition to the input node feature, as you can see from here. Basically, they add additional node level features in addition to their nodes, and then they do this linear transformation as their input. So this paper is going above this paradigm. They actually do something more than this. And what they did in addition is that they update this term jointly as you go through layers of GNN. You can see here, you kind of not really doing that, but here they're updating this jointly. So, and yeah, they also experiment with different choices of the initial positional encoding of each node, and they end up choosing this k-step random walk matrix as their additional node features.
So for the P, it's learnable like kind of vector, right?
You mean P? Yeah, P is
Yeah.
learn.
And it's always fixed. Does it have the layer information?
Does it have layer information? So,
I do see this L.
yeah, it's updated at each layer.
Does that mean that for each layer, the position encoding will be different?
Yeah, for each layer, the positional encoding will be updated, so it will be different. Yeah.
Okay. Yeah. So if we don't have that layer index, then it's kind of similar to we try to also add this shallow embedding, and it's learnable. But now they say that okay, they want to do it for every layer.
Yeah, this is indeed the key for their paper, is to add this layer-wise update for the positional encoding.
Okay, then why is it called a position encoder, right? Because it's just some sort of kind of learnable latent features.
So
Whether it's related to position or not, it's unclear.
yeah, if you're talking about position in the geometric sense, for example, if you're talking about coordinates, right, then perhaps this is not really a coordinate type of thing. Yeah. So yeah, indeed, I think at this step to call it positional encoding is kind of a stretch. It's basically some, I think, some graph level additional features, yeah, structure information.
Okay, and also it seems to me they make it the design choice to have the same dimensionality for P and H.
Yeah, they have, yeah.
Okay,
Yeah,
they just
SDK.
want to understand whether it's ad hoc or whether they have done lots of careful evaluation study and then they finally make this choice.
They didn't really specifically talk about how they get this dimension. They didn't really do that.
Okay,
So basically, by doing this, they actually outperform the previous transformer case, which, by the way, is called graphformer. They outperformed that one on the biological data sets and the chemistry data sets. Yeah. So kind of, and then they say that the random walk positional encoding is better than the Laplacian one. Because yeah, so basically, for these papers, for the transformer one and this one, they didn't really talk about the information bottleneck. So the information bottleneck was something that was introduced later on. The reason why I'll talk about this is because I think implicitly they're also addressing this problem because they're changing the computation graph, they're changing the receptive field. They didn't really mention the bottleneck problem. Yeah, that's a very good question. Thank you. And basically, I just want to say, if you want to use transformers, then you need to do positional encoding, and they provide ways on how to do that. And then this paper will be related to a later paper I talk about, which also involves the positional representation and the feature at the same time, but do it in a continuous way. Yeah, let's. Okay, so far we have seen this heuristic-based rewiring approach, right? There is not a lot of theory going on. People just add connections, or they just use full connections and they add positional encodings. So what's interesting about the previous paper, which involves the positional encoding, is that if we, this is something that Professor Sun mentioned, right? Because when we think about positional encoding, we kind of think about the relative positional information between the nodes, and we kind of, if you think about like a Euclidean space or any geometric space, we kind of think about the coordinates of each node. So that would be considered positional. So naturally, I think this positional encoding kind of implies a geometric perspective about the graph problem. So this opens the door for the manifold-based perspective. And then the random walk is an operator, as we shall see. It's like a discrete diffusion process. So this also opened the theory of PDEs to be introduced. So here, there will be two mathematical tools we use to formalize this graph rewiring problem in a more theoretical fashion. First would be the diffusion PDEs, and the second one would be differential geometry. So first, I want to go to the diffusion on the graph. So this paper in 2019 basically have a very simple pipeline to do their graph learning. They didn't change anything about the GNN. Only thing they do is this pre-processing step to change the input graph by going through some random walk and continuous discrete diffusion. So they start with the input graph. They do a bunch of diffusion process, and they get a denser graph. They sparsify this dense graph, and then they use this resulting graph as the computation graph. We will briefly go over this paper later. So first, I just want to review what we mean by diffusion on the graph. So this perspective is to view the entire graph as a state of a Markov chain. And we kind of view each neighborhood relationship of basically a node and its neighborhood. We define a kind of probability distribution. The unnormalized one we generally term as a kernel. So the transition kernel of a graph, they come in different flavors. This one is called the random walk transition. It's basically you have your adjacency matrix, you have the degree matrix, and you divide your adjacency matrix terms using it by the degree. It's basically some basically you weight the transition probability from one node to its neighbors by the degrees. And then the second one is called the symmetric random walk transition. This one we kind of familiar with. It's appeared in the context of the normalized Laplacian as well. So yeah, and then the third one is to add in some inner loop, and then add in some inner loop, basically the loop, this is called the loop probability. Basically it means the probability of a node stay rather than going to any of its neighbors. So that's why it is called lazy random walk. And then the generalized diffusion on graph is basically you sum up all the possible k-step diffusion, where T is the general transition kernel. And the theta k's were called diffusion coefficients. Basically, they determine how strong is the diffusion at each k. So already in the network analysis literature, there exists some kernels that have very nice properties that enjoy closed form representation for this infinite sum. One of them is called the personalized PageRank kernel, which has this form for its diffusion coefficients, and use the random walk transition kernel. And then the heat kernel is another one, which uses, again, the random walk transition kernel, and uses this kind of exponential term for the coefficients. And you can see very intuitively, the bigger your, so T here is a temperature. Yeah, so I think one interesting question to ask is, what happens if K goes big? I think in all these cases, when K goes big, the diffusion coefficient should be very small, because this means we should really care about the short range interactions more than the long range interactions. So the long range ones, we sort of think about, if they're too far away, they shouldn't affect your node too much. And this is also known as smoothing property of this kind of process. And you can kind of see why these two kernels have these nice properties, because the exponentials and the geometric series, they converge if you do infinite series sum. So the special case of this is resulting in the heat kernel. And this is basically telling you that, screaming at you that this has something to do with PDE, because the heat equation's fundamental solution in PDE is the heat kernel. And later on, you will see some ideas on using this framework to reason about GNNs. The paper graph diffusion convolution, they basically do this. Basically do this rewiring process by using a diffusion kernel to evolve the initial adjacency matrix, which they obtain this final adjacency matrix S, and then they sparsify the graph, and then they apply the spatial GNN on this S. So in this way, they claim that they combine the spectral and the spatial approach. So the spectral approach is the the heat diffusion approach, and then the spatial approach is to use GNN to learn. This is a very early work, so the benchmark and the results they get is only here for reference purposes. They basically want to show you that if you add this additional pre-processing step of graph diffusion, you can achieve better performance than if you simply use spatial GNN. And as I mentioned earlier, there you see the heat kernel, and then you can sort of think about, if we have that perspective on graph, can we use PDEs on graph? So this paper is the one that I will introduce later on, the Beltrami flow and the neural diffusion. So we see that diffusion is important. And this one applies diffusion to the joint space of feature and the graph structure. Actually, here the graph structure means positional encoding. So this is also tied to this paper, which we talk about co-evolving the positional encoding and the features. So so the key idea one is that we want to modify the graph structure while exploiting the diffusion as an inductive bias. And then we want to model both the structure and the feature information. So before I go to this paper, first we need to formalize what we mean by doing diffusion, like in the context of GNN. So this paper in ICML 21, they hypothesized that the GNN structures, architectures, how we do message passing is basically a discrete diffusion process, where we discretize a PDE. So how do we do that? We first define the discrete analogy of the differential operators. For example, we define the gradient of X to be the difference between the node feature of two nodes. This is, and then we define the divergence operator of this. I think is the node feature. So you can see gradient is with respect to an edge. Divergence is with respect to a node. So divergence in physics is basically means the infinitesimal flux of some quantity into the volume. So in the context of graph, this would mean translate to the messages you pass from the neighbors into the central node. So naturally, if we take this perspective, we can think about message passing GNNs as a special case of a discrete version of like this diffusion process. So if you write this PDE into the discrete format, for example, using the Euler scheme, you have this kind of discretization. The gradient operator becomes this discrete difference between the node embedding from layer K and one layer above. And this is proportional to the difference between the same layer and the some like a scaling term, which we can see is very similar to attention, which corresponds to the omega here. So
but this slide is very interesting, but I'd like to understand how the first, where does this first formula come from?
You mean this one?
Yeah.
Yeah, so this is known as the diffusion equation. It's a PDE.
So for the standard diffusion process, are they defined over graphs?
Yeah, so basically there's an even easier way to write this. If G here is 1 or a scalar, then the divergence of gradient is the Laplacian. So this is the simplest case. It's called homogeneous diffusion. And this is basically similar to what we have when we have a spectral understanding of the graph convolution, right? We sort of think about the graph convolution as this Laplace operator on the nodes.
I guess my question is like, if we think about the diffusion process defined in a non-constrained space, for example, a 2D space, right? You try
Yeah.
to understand like how the heat will diffuse over the space along the time.
Right.
So in that context, we don't really have the graph there, right? But I think that might help us to understand the the diffusion process in the standard physical system. And then we'll move to the graph setting. Because that G, when you say GXT, right, I don't really understand what that means.
Yeah, so let me talk about what this GXT means. This is what is known as the diffusivity or the diffusion coefficient. It is talking about how intensive is the diffusion. So if it's a scalar, let's say if A is big, this means we have a very strong diffusion and so on. Yeah, that's what it means. So simply, if you represent it in this way, it basically says that the strength of your diffusion depends on the both time and space. It depends on both the node feature and the layer of your GN.
I see. So G will take XT and T as input and
Yes.
output something. And it could be just some constant like A.
Right. So if we think about the standard GAT, right, this is actually GAT is actually, I think, a very interesting way to understand this scheme, because GAT is basically asking you what's the relationship, how strong is the relationship between a node and its neighbors. So that corresponds to the strength of the diffusion in this sense. And in the most general case, your graph attention matrix, the tension between a node and its neighbors, they could change as among different layers of GN. And that would represent the most general case of the diffusion equation. Does that make sense?
Yeah, but still appreciate if we can have the original version of differential the PDE for the diffusion process. That would be even more helpful.
I see.
Yeah. So for example, for the XT here, right? So in the graph setting, we can easily understand that, okay, this X has to be a vector and the dimensionality should be the number of nodes in the graph.
So XT here, I think is actually not, it should be, if we talk about the entire graph, then this one should be a matrix of number of nodes times the number of features, right? Now, if we talk about one node, then this is indeed true. Yeah.
Then for this XT, are we talking about one node with d-dimensional feature, or we're talking about a collection of nodes?
We can talk about I think we can talk about a collection of nodes. That's assuming that X here is the entire feature matrix of the graph, right? So that would mean it's n times d. It's a matrix. And here we can say this would be a d-dimensional vector, even so they use this this one. Yeah, we can say this is a d-dimensional vector. Basically the difference between the node features.
Yeah, graph is like provide a discretized structure, but in the original setting, if we don't have that graph, essentially the diffusion process can happen in any direction.
Right, that's why they do this analogy of using the graph structure here to compute the divergence.
What does divergence mean here?
So divergence, so in physics, divergence means if you have a infinitesimal volume, for example, and you have a electric field, for example, let's say, then divergence means in this volume, how many like electrons are there, something like that. It's basically talking about, so this concept is called flux. Yeah, it's a little bit difficult to talk about. It's basically like in the graph case, you just think about it as aggregating messages from the neighbors to the central node.
Yeah, it definitely it's easier for us to understand from the graph perspective, but I think this slide tried to make the connection between like a general diffusion process and something defined on the graph. Right? So that's why I think a deeper understanding on the Orange setting is also very important to help.
Yeah.
Yeah, we kind of understand the second part. It's just the first part, the Orange setting is not that clear.
Well, I think mathematically, even though intuitively there might be some difficulty, mathematically it's very simple, because when you try to discretize this PD with the Euler solver, then you naturally get this this expression that looks like one layer update of your GN.
Mm.
Yeah, I think that's the most important part.
Yeah, because if you think about diffusion, right? So your kind of your local heat will be updated based on your kind of local neighbors. This kind of weighted average, right? So because the heat is going to they're going to exchange or something. So from that part, it's kind of understandable, but it's just that the original formula not that clear.
Okay, should I go on with the slide?
Yes, please. Yeah.
Thank you. Yeah, so basically in this paper, it's called a grant. They simply view GN as a discrete PD, diffusion PD, but they didn't really talk about positional encoding or graph rewiring. So the later paper by the same author, I think even in the same year, one on SCML, one on NeurIPS, kind of using the same framework applied to positional encoding as well. So the idea is to not simply do diffusion on the features, but also do diffusion on the structure. So the motivation comes from image processing. So basically, we can sort of think about the image as a joint space of the pixels and the pixel coordinates and the RGB pixels. If we're talking about two-dimensional image, then if we're talking about image, then it's two-dimensional. Then each pixel has a 2D coordinate, and they also have like a RGB 3D representation. So in the end, we have a 5D. And we can sort of disregard this language here. They say they treat it as a manifold and so on. And then they apply the diffusion to this joint space, which is actually as we can see, the easier way to represent this equation, which is we have the time derivative, and there's a Laplacian on the right hand side. And this is basically when you use the language of manifold, you instead of using the Laplacian, you talk about it like a Laplace-Beltrami operator. So the key idea is that now we, instead of only dealing with the X, now we also want to deal with A. But we can't really deal with A, because A is a discrete object, and that's why positional encoding comes in. So this is still talking about the image case. In order to make the Laplacian operator work, you need to do some math to compute the infinitesimal volume. What do we mean about the infinitesimal volume in the manifold? So they have to define the Riemannian metric tensor and then defining this infinitesimal map. Yeah. So in the end, they have this formula for their diffusion equation, and we can see that there is a term here. This is, as I mentioned earlier, this is called diffusivity, which is governing how strong is your diffusion at each point in space and time. So a property of this equation, which is called the Bertrami flow, is that it is trying to preserve the edges while performing denoising. So it is an instance of non-homogeneous diffusion. Non-homogeneous diffusion means that you have different diffusion intensity in different spatial coordinates. If you, for example, see that the homogeneous diffusion, it doesn't really make any distinctions. It just basically makes everything more blurry. But with this Bertrami flow, they're able to kind of detect the edges, and then they only, they only diffuse the edges. So that's the thing. That's how this Bertrami flow is different from the standard Laplacian equation, for example. And then again, you make this same analogy from the continuous space to the graph. And again, the only thing you need to worry about is the change in divergence. So divergence now is in a discrete version, it's basically the aggregation of messages from the neighbors to the central node following the graph structure. So what they do here, in addition to diffusion on the feature, as I mentioned, is they also do diffusion on the positional encoding. So X here represent the feature of your nodes, and the U here represents the possible positional encodings you have for your node, and they want to update both of these jointly use this diffusion process. So you can sort of imagine this one as a continuous version of the paper that we introduced earlier, which is, discretely evolving them. And I think with this, this basically, again, reiterating the relationship between this formalism and the graph neural networks. Yeah, so the Bertrami flow is basically a variant that also performs graph rewiring. And here is the detail of their formalism. They use this attention. So again, this attention is like the standard GIT formalism of attention, which controls the intensity of diffusion for different nodes. And then because they have this PDE formalism in continuous way, they actually use a neural ODE to go through the modeling process. And they provided some preliminary results on the performance. And I think it is always tricky to look at the results of these continuous models, because not necessarily they would outperform all the baselines, as you can see in this case. There are some like, but then it's just like some small scale study of the effectiveness of these formulas. I think for me, the more important thing is not really the results, but the idea of using some mathematical tools to principally update both the feature and the graph. And this opens a door for even more interesting geometric perspective, because the PDE is defined not just in the Euclidean space, but in any general manifold. So if you can do embedding of your graph in a hyperbolic space, then the coordinate of the nodes would also correspond to positional encoding, which would also make sense to use the Bertrami flow or any reasonable PDEs to evolve. So Bronstein, I think, is a very big hypothesizing that graph could be potentially viewed as a manifold, and that would open the door for more powerful mathematical tools to be used. The last topic I want to talk about is again from a geometric perspective. And this one is directly addressing the overstretching phenomenon that we talk about. Remember that all we want to do so far is we want to modify the graph structure to address this problem. So this paper gained insight from differential geometry with a construct for the Ricci curvature, and they kind of want to apply the analogy of Ricci curvature to graph, and then using this ODE called the Ricci flow to evolve the graph structure. So you may have seen Ricci flow before in news. It is, I think, one of the very important tools used to solve the Poincare conjecture. So first, we do some little bit of review of what is a curvature. So so basically, if you have two straight lines, let's say of x and y, right? In this case, then the difference between, so the distance between x, y would not change as you progress, right? It will be the same here because you have a parallel lines. But if you have two curves, then the distance between x and y would actually change as you progress, right? So the idea of a sectional curvature is basically talking about if you go if you go from like x to its tangent vector's direction for some time, how it would affect your the distance between these two points, right? So, and the Ricci curvature is basically a generalization where you take expectation for all the possible directions at x and at y. So this in 2007, Olivier proposed an analog of Ricci curvature for graph. Basically, they try to, instead of think about it continuously, they think about graph as some sort of a distribution, because you see like, yeah, I think, yeah, basically for each node, you can describe its neighbors using some sort of a distribution. That is the idea of kernel, right? And we can sort of think about how do you move the how do you measure the distance from one neighbor to another using the Earth mover distance, and that is the also known as the Wasserstein distance. So and here is basically just the formal description of what this means. So they define the Wasserstein distance here, and then they define the curvature as this, yeah, as defined it as this. So this one, so I think right now it looks very abstract, but D here basically, if we think about the graph as a metric space, then D here would mean the shortest path distance. And I will give an example of what this W1 means in the next slide. So if we look at this left grid, and we look at this one in the middle, like we have, so what would be the cost of transporting from this one to this one, from this neighborhood to this neighborhood? So in this case, you simply do like a horizontal shift. So for example, let me see. Yeah, so let's see. So dxy is compared against. So if we want to move y2 to x4, I think yeah, I'm a little bit lost right now. Yeah, so basically, I think what we want is for this one to equal to 0. And for this one to equal to 0, that means the Wasserstein distance equals to the shortest path distance. Because this is a grid, it's a grid so corresponding to a Euclidean space. So dxy here is 1. It's the shortest path between these two. Then what would be the Wasserstein distance between its neighbors and this? So yeah, I probably will need to.
Yeah, I think I don't know the range of the Wasserstein distance, probably because it tries to define the distance between two distributions, right?
Yeah, it's trying to define.
Okay, so and for the shortest distance, are you sure that dxy is the shortest distance?
Oh, actually, yeah. So if we understand the Wasserstein distance as the optimal transport distance, which is how do you move from one distribution to another, then in this case, you simply right shift the entire thing by 1. So the Wasserstein distance in this case is 1, and the shortest path distance between y2 and x4 is also 1. So that's why this term equals 0. Yeah, does that make sense?
So want to calculate curvature.
Yeah, so K is the curvature. It's just that in a metric space, they use this way to define curvature.
Yeah, so we don't want it to be anything. It's just based on this formula we can calculate. It's kind of definition.
Yeah.
It could be anything.
Yeah, it
Okay.
can be anything. It's just that in this case, it should be 0 because it's a grid. So yeah, so basically, they make this analogy of manifold to graph. And if you have a flat space, you would have a grid. And then if you have a hyperbolic space, you would have a tree which have a negative curvature. And if you have a sphere, a kind of a sphere which has positive curvature, then it's a clique or a fully connected graph.
I remember somehow for those 3 examples, if we utilize curvature, I guess it's called Gaussian curvature. So we're going to have the same conclusion, negative, 0, and positive.
This is we define curvature using this notion of a sectional curvature.
Then what's the advantage of this curvature compared to the curvature definition, like Gaussian curvature? I think we had that. Yeah, we learned that in the reading group.
The reason why
on differential geometry, right?
Is because we want to use this Ricci curvature, and the Ricci curvature is defined as the expectation of sectional curvature. So Gauss curvature is not used here. Yeah, I don't think there's any advantage. It's just that you have the goal is to use this, so you kind of use this.
That there is something about Ricci curvature which can be like some operation which work better on.
Yes. Yes. Because in the end they use Ricci flow, so that's like, and then we can sort of see the bottleneck here. If you have a tree, right, then definitely this one is the bottleneck. Because all these nodes has to go over this one node in between to pass messages. So one important observation in their paper is they say that the bottleneck of a graph come from negatively curved nodes. And here is another, I think, explanation about the Ricci flow on graph. So Ricci flow basically it's ODE that describes the evolution of the Ricci curvature. So what it's doing is it's kind of scratching this negative curved part and augmenting the positively curved part. So and you can see that positive curved parts are these fully connected ones, and the negative ones are like the links in between. So if you have a community graph with different communities, so naturally, if you apply this Ricci curvature, Ricci flow, you get a very natural way to do community detection. So this is actually a paper in 2019 that using Ricci flow to do community detection. So they kind of use this same idea, because you see with the bottlenecks in graph, you want to add more connections whenever you see a bottleneck. But when your graph is already pretty dense and well connected, you don't have to do a lot. So they simply use this intuition to do graph rewiring by adding more connections whenever there is a bottleneck. And in their practical implementation, they used another more efficient version of the Olivier curvature, which is really technical, and I don't think it's worth covering here. But the key observation is that the negatively curved edges are responsible for the bottleneck. And they can determine some threshold for how negative it should be to do some graph surgeries. So they add edges when the curvature is too small, too negative, and they sometimes also remove edges when the maximum curvature is too big. Yeah. So yeah, that's their main algorithm. So the algorithm is actually pretty simple. It's all pre-processing step for the graph. They didn't actually do any modification for the GN. Yes, and then they provided some results. So this one here is plus FA here. Is as you might remember, this is the first paper we covered, which is basically you change the GN by adding full connection in the last layer. And this DIGL here is the graph diffusion convolution paper that we covered. Basically, you use the diffusion kernel to do pre-processing. And I think here is their own proposed approach. And they show that on the existing on some of these data sets, they have better performance than the other rewiring methods. But again, I think what's really interesting about this paper is their perspective rather than their results. Their results are good, but not like consistently better in all cases. And then I think here they try to they try to see how this graph rewiring process changes the distribution of the graph. And they reason that using their method, it actually does not shift the distribution of the graph a lot. Whereas if you use the diffusion-based method, it's gonna shift the graph distribution a lot. So they argue that using their way is like a more stable representation in this way. So yeah, that's like all the papers. So here I just want to summarize what I go through with 3 observations. First observation would be the motivation for graph rewiring. It's basically saying that your original graph topology often not optimal, so you do some rewiring, which either involves decoupling the computation graph with the original graph or doing some surgeries. However, you cannot simply disregard the original topology. Even if you, for example, use a transformer and a fully connected graph, you need to add positional encodings. And then the third one is that recent work has opened door to view graph as a more geometrical object, and which would open the door for more rich set of mathematical tools. Yeah, that's everything. Yeah, thank you. Are there any questions?
Thank you, Fred. I think the last two work are indeed very interesting. So probably we need to give them a like more thorough reading because some of the definitions are not that clear to us. But my feeling is like lots of things can are hiding there, right? So and we can learn a lot from them. For
Right,
example,
I think a big problem with this paper, I think, is that if you read their paper, it's actually a lot more confusing. They have a lot of terminologies that's hard to grasp. So
Interpret the graph as from a pure topology perspective.
no, it's not topology. It's
Geometry.
geometry,
In
yeah.
geometry topology perspective. Or they don't call
no,
it.
they don't talk about topology at all.
I don't think it's about how they come just to citation.
Yeah. Yeah, it's more differential geometry.
yeah, that's related to our earlier reading group. However, we need to revisit those concepts. For the second work, for example, we have this Olivia curvature.
Curvature. Yeah.
I think it's very interesting because earlier I think Yawen and we thought about like this graph manifold could be very complicated. The curvature could be very different at each local node, right? So then how we can handle that? So right now, of course, most of the graph neural networks do not really consider the curvature and they just apply the standard method passing and most likely with assumption that everything's in the Euclidean space. But more recent work says that, oh, we need to consider like non-Euclidean geometry. But then somehow they still assume that, for example, with constant curvature or something like that, right? So here it's more like if we have this very weird geometric object with different curvature at different places, then how we can design our graph neural network.
Yeah, so I think Roshni had a paper recently, right, on geometric embedding of a knowledge graph with different different curved spaces. So I think it's just that it's a very interesting perspective. It's just that I think what's more interesting is that you have this geometric representation. The next step is to evolve this representation. You don't treat it as a static representation. So that's where diffusion comes in. That's also very important.
Yeah, and also, yeah, so for Russian work, right, just wanted to further comment. If you think about that, it's like two constant curvature spaces there, like have some intersection. But that our graph could be more complicated than that. Just like each local region has a different curvature, and then we probably need to really model that. Another thing I think related to the diffusion, right? So, yeah, if the the manifold is very complicated, when we do the diffusion, just like the speed is going to be different, right? Yeah. So how we can model that? Yeah, I think lots of things can be. If we go deeper, lots of things can be done.
Right.
Okay, so that's my comment. Yeah, thanks for introducing all those papers.
Right, thank you. I guess that's all. Thank you all for joining me today.